What if I told you that our solar system is a cosmic anomaly? That among the thousands of planetary systems we've discovered, ours breaks nearly every rule we thought we knew about how planets form. Today, we're diving into why our little corner of the galaxy might be far more special than we ever imagined. Hey, space enthusiasts! For decades, astronomers assumed our solar system was pretty typical. 8 planets orbiting a single star in neat, circular paths. But as we've started finding exoplanets by the thousands, we've discovered something shocking. Systems like ours are incredibly rare. So what makes our solar system such an outlier? Let's start with something that shouldn't exist, according to most planetary systems. Our gas giants are in the wrong place. In most star systems, massive planets called hot Jupiters spiral inward during formation, ending up incredibly close to their parent star. These scorching gas giants complete orbits in just days or weeks. But Jupiter, it migrated inward, then mysteriously reversed course and moved back out. This grand tack model explains why Jupiter sits comfortably at 5 astronomical units from the Sun, taking 12 Earth years to complete one orbit. Without this bizarre U-turn, Earth might never have formed, or it could have been consumed as Jupiter spiraled toward the Sun. Even weirder, Saturn followed Jupiter outward, creating a gravitational dance that sculpted our entire solar system. This planetary ballet is so unusual that finding another system with a similar migration pattern is like winning the cosmic lottery. Here's another way our system breaks the mold. We don't have super-Earths. These planets, roughly 2 to 10 times Earth's mass, are the most common planets in the galaxy. Almost every star system has them, orbiting close to their parent star. Our solar system, zero. Nada. We jump straight from tiny Mars, at 0.11 Earth masses, to massive Jupiter, at 318 Earth masses. There's nothing in between. Most astronomers think Jupiter's early inward migration actually prevented super-Earths from forming in our inner solar system, clearing out the material that would have created them. This absence might be crucial for life as we know it. Super-Earths often have thick atmospheres that create runaway greenhouse effects. Their absence in our system allowed small, rocky planets like Earth to develop moderate climates perfect for liquid water. Most exoplanets travel on highly elliptical, egg-shaped orbits that swing them from scorching hot to freezing cold. Some have orbital eccentricities so extreme they're basically cosmic comets. Our planets, they're almost obsessively circular. Earth's orbit varies by only 3% throughout the year. Mars, our most elliptical planet, still maintains a relatively stable orbit. This stability creates consistent seasons and climates that have allowed life to evolve and thrive over billions of years. The reason for this unusual stability, probably Jupiter again, its massive gravitational influence acts like a cosmic shepherd, keeping the inner planets in line and protecting them from gravitational disruptions that would send them careening into chaotic orbits. Between Mars and Jupiter sits something that shouldn't exist in most planetary formation models: a stable asteroid belt. In most star systems, this region would either be occupied by a planet or completely cleared of debris. Our asteroid belt represents failed planet formation, material that never coalesced into a single world because of Jupiter's gravitational interference. But instead of being flung out of the system or consumed, these rocky remnants found a stable gravitational sweet spot. This cosmic junkyard has actually been beneficial for life on Earth. While asteroids occasionally impact our planet, the belt also acts as a source of water and organic compounds. Some scientists believe asteroid impacts delivered the building blocks of life to early Earth, making our failed planet an unlikely hero in the story of terrestrial life. Perhaps most remarkably, our solar system has what astronomers call the Goldilocks Architecture. Everything is positioned just right. We have small, rocky planets in the inner system where temperatures allow liquid water, and gas giants in the outer system where they can act as gravitational vacuum cleaners, sweeping up dangerous debris. This isn't just lucky, it's extraordinarily rare. In systems with hot Jupiters, massive planets dominate the inner regions, making Earth-like worlds nearly impossible. In systems without gas giants at all, rocky planets face constant bombardment from asteroids and comets. Our configuration, with Jupiter and Saturn positioned as outer guardians, while leaving the inner system clear for small, stable worlds, appears in less than 1% of planetary systems we've observed. Here's something that might blow your mind. Our moon is absolutely gigantic compared to Earth. Most moons in our solar system are tiny compared to their parent planets, like cosmic pebbles orbiting boulders. But our moon is about 27% the diameter of Earth, making the Earth-Moon system almost like a double planet. This size ratio is virtually unheard of in the universe. The leading theory is that early Earth was struck by a Mars-sized object called VA, and the debris from this cosmic collision eventually coalesced into our moon. But here's the kicker. This impact had to happen at exactly the right angle, speed, and timing. To direct, and Earth would have been destroyed. To glancing, and no moon would have formed. Our oversized moon does something incredible. It stabilizes Earth's axial tilt, preventing dramatic climate swings that would make complex life nearly impossible. Without the moon, Earth could flip between ice ages and scorching periods on timescales of thousands of years. Mars, which lacks a large stabilizing moon, wobbles chaotically and experiences extreme climate variations. Our moon is essentially life's guardian, keeping Earth's climate stable enough for evolution to work its slow magic. Finally, there's the question of long-term stability. Our solar system has maintained its basic architecture for over 4 billion years. The planets haven't migrated significantly, collided, or been ejected into interstellar space. This stability is incredibly rare. Most planetary systems show evidence of dramatic instability. Planets with retrograde orbits, misaligned spin axes, or orbital periods that indicate violent past interactions. Some systems have planets orbiting backwards compared to their star's rotation, suggesting massive collisions or gravitational ejections. Our system's boring predictability over geological timescales has allowed life to evolve, adapt, and flourish without facing constant existential threats from planetary chaos. So there you have it. Our solar system isn't just unique, it's profoundly weird compared to the cosmic norm. From Jupiter's impossible U-turn migration to our missing super-Earths, from perfectly circular orbits to a stable asteroid belt, and from our oversized moon to billions of years of stability. We live in a system that breaks nearly every rule of planetary formation. Does this make us special? Maybe. Does it make us alone? That's still the biggest question in astronomy. But one thing's certain, we're living in a cosmic rarity. A planetary system so unusual that finding another one like it might be the discovery of the century. What do you think makes our solar system special? Let me know in the comments below. And if you enjoyed diving into the cosmic mysteries that make our home so unique, subscribe for more space content and hit that notification bell. Until next time, keep looking up.